Hello friends, here in this video we will see a problem on helical compression spring for a given range of operating pressure. What that means, to understand it better, let us have a question here. I'll read what is given here. Design a helical spring in compression for a spring loaded safety valve for the following conditions: operating pressure 1 Newton per mm square, maximum pressure when valve blows off, it is 1.05 Newton per mm square, maximum lift of valve when the pressure is 1.05 Newton per mm square, maximum lift is 6 mm, diameter of the valve seat is 100 mm, tau max, maximum shear stress, it is 400 megapascal, G, that is modulus of rigidity, 86 kilonewton per mm square, and spring index, that is 5.5. So for these conditions we have to design a helical spring. Now whatever is given in this problem, I will write that in the form of data first. Let us get started. Now in the data I'll write down, here we have to design the helical compression spring. So the question is design of helical compression spring. For the spring loaded safety valve for following conditions, operating pressure is given 1 Newton per mm square. So operating pressure I denote it by P, that is 1 Newton per mm square. Next, maximum pressure when the valve blows off. So this is P max value. I'll write it as P suffix max, that is 1.05075 Newton per mm square. Next, maximum lift of valve when the pressure is maximum. Maximum lift, this maximum lift means when the valve gets lifted, spring will be deflected by 6 mm. So this is the maximum deflection of the spring. Maximum deflection is 6 mm. Diameter of valve seat is 100 mm. So I'll denote it by capital D. Tau max is 400, maximum shear stress. 400 megapascal, that is Newton per mm square. Capital G, modulus of rigidity is given 86 kilonewton. So I'll convert it, it is into 10 raised to 3 Newton per mm square. At last, spring index, that is 5.5. Spring index is denoted by C. Now for these data given, let us try to get the solution for this problem. In the solution, I'll say that the problem is different. Here, instead of giving the load directly, they have given us two values of pressure. So from these values of pressure, I would be calculating the individual loads. So first, since this is the operating pressure, so I'll calculate operating load. So I'll say that since operating load is given by, I'll denote it by W1, and that will be equal to operating pressure multiplied by area of the valve. Very important conclusion here. This relation I have got, since I can say that pressure is equal to load upon area. So here I am writing the operating load. that is pressure into area. Therefore, W1 will be equal to, pressure is 1, area pi by 4 into diameter square, diameter of the valve is given as 100, so 100 square. So from this I will get the value of W1 and my answer is, it is 7850 Newton. This is the operating load, that is the minimum load required to operate the spring. Next, I'll say that similarly, maximum load is given by, that I'll denote it by W2, and it will be again maximum pressure. Here this will be maximum pressure into area of the valve. Since they have given us maximum pressure, so we can use this value to get the answer of maximum load. So it is 1.05, therefore W2 will be 1.075 multiplied by area of the valve, that is again pi by 4 into 100 square. So from this I'll get the answer of W2. I'll write it onto the next page. W2 value comes out to be 8443.03 Newton. So after getting these two values, W1 is 7850 and W2, these are the load range. So in this problem they had given us the load range in the form of pressure difference, that is operating pressure and maximum pressure. So I'll say that therefore load for which spring is to be designed, that load will be capital W and it will be equal to W2 minus W1. Since W1 the value is 7850 Newton and W2 it is 8443.03 Newton. Now this is the load range. So here it means that on this spring the minimum load will be 7850 Newton, maximum load would be 8443.03 Newton. So this is the load range for the given spring, and we have to design the spring for this load range. So load range is W is equal to W2 minus W1. So from this I'll get the answer of W as, which I have already calculated, and my value is 593.03, which I can say it is very close to 595 Newton. So I'll design the spring for 595 Newton. I'm designing it for some extra value of load. Now after getting this, I'll say that since deflection of spring, deflection can be written as load upon stiffness. So from this I can get stiffness, therefore K will be equal to load upon deflection. I'll use this formula. From deflection I can get stiffness formula. Now I'll write the value onto the next page. So therefore K, it will be equal to, load is 595 and deflection is given in the problem as 6. So here stiffness comes out to be 99.17, or I can say this value is very close to 100, so it is 100 Newton per mm. This much is the stiffness of the spring. Now After getting stiffness, I'll say that since shear stress factor is given by shear stress factor is K suffix S, that is equal to 1 plus 1 upon 2C. So therefore here I can write it as 1 plus 1 upon 2C. C is 5.5. So from this shear stress factor value, it comes out to be 1.09. Now after getting the shear stress factor, if I look into the problem, then shear stress is given, and this shear stress is maximum, or we can say resultant shear stress. So I'll say that therefore resultant shear stress, it is tau is equal to 8 WD upon pi d square multiplied by Ks. And here we have d cube, not a square. So it is 8 WD upon pi d cube into Ks, which is the shear stress factor. Now I know that capital D upon small d, that is equal to spring index. So I'll replace this by C and write it as, this formula will change. So therefore shear stress will be 8 WC upon pi d square into Ks, shear stress factor. See why I am using this value of C, because in this problem we don't have the value of capital D and small d, so we cannot find any other value, that is two unknowns are there in the same equation. So if I have any one value, I can calculate the other. So I am replacing capital D and small d by C. So therefore, since we want to calculate d square, or I'll say diameter of wire, d square would be shifted here, and here I have 8 WC upon pi into tau multiplied by Ks. 8 into W, the value of load range, it was 595, into C is 5.5, pi into tau, resultant shear stress, it was 400, into Ks, and Ks was 1.09 shear stress factor. So from this, first I'll get the value of d square. D square comes out to be 22.71, and if I take the square root, I'll get the answer of D, and my answer is 4.76, or I can say 6 mm. So here this is the first answer. We have calculated how much should be the diameter of wire used for this spring. So here we will use a wire having diameter D is equal to 6 mm. Now, once I have calculated the diameter of wire, I can even calculate the mean coil diameter. So I'll say that since capital D, that is the mean coil diameter, it will be equal to spring index multiplied by small d. Here I am using this relation because C is equal to capital D by small d. So therefore capital D will be, C is 5.5 into D, which is 6. So diameter comes out to be 33 mm. This will be our second answer. So here we have calculated wire diameter, mean coil diameter. The next thing is, we will use the deflection formula to get the total number of active coils. I'll say that since deflection is given by, deflection is equal to 8 W D cube N upon GD raised to 4. This is the formula of deflection. Here in this formula, either we can put the value of capital D or small d, or we can change this formula in such a way that capital D by small d is C. So that would be C cube N upon GD. Here I can say, since C is equal to capital D by small d. So therefore, I want to calculate N. N will be, this GD will get multiplied with deflection. So deflection into GD upon 8W into C cube. Deflection, it is given in the problem as 6. G is 86 into 10 raised to 3. D, it is 6 upon 8 into W 595 into C cube, which is 5.5 cube. So from this I'll get the answer of N. It comes out to be 3.90. I'll round it off to 4. So I'll say that therefore number of active coils, that is equal to 4. This is our third answer. Active coil means these are the coils which take part in the actual compression. So apart from this, we need to even have total number of coils. So I'll write down therefore total number of coils is equal to number of active coils, I'll denote it by N, plus 2. Here I'll write down assuming squared and ground ends. So therefore total number of coils, I'll denote it by N dash. So N dash will be equal to N plus 2, that is 4 plus 2, and hence N dash is equal to 6. So here I get the total number of coils. This is our fourth answer. Now after getting the total number of coils, I can get the solid length. So I'll say that therefore solid length of spring, solid length will be equal to N dash into D. Therefore solid length becomes 6 multiplied by D. We have got the value as small d was, it was 6. So here I get the solid length as 36 mm. This is our fifth answer, that is the fifth parameter which we have calculated. Now what is solid length? It can be explained with a diagram. That suppose we have a spring which is supported at two ends. So here this is the solid length. It indicates the length of spring when the spring is compressed in such a way that each of its wire diameters, they are in contact and there is no gap in between the spring. That is the length of the spring in the closed condition. So solid length we have calculated. After this I'll write down free length. Therefore free length of spring LF is equal to solid length plus maximum deflection plus 0.15, that is 15% of maximum deflection. Now here free length formula I have written, so I'll put the values in this. Therefore free length will be equal to solid length, it is 36. Maximum deflection is given in the problem, it was 6 plus 15%, that is 0.15 of maximum deflection, that is 6. So here I get the free length value. It comes out to be 42.9, which you can say it is close to 43 mm. This will be the sixth answer or the sixth parameter which we have calculated. Now what, after getting the free length is the spring length in the unloaded condition, that is when there is no load on the spring. So the last thing which is left, that is pitch of spring, and pitch can be calculated by the formula free length upon n dash minus 1. So here free length is 43, n dash it was 6 minus 1, so therefore pitch value comes out to be 8.6 mm. Now this is the 7th parameter which we have calculated. Now once we have calculated all these parameters, I can draw the helical spring. I can draw the diagram and explain. Here is the diagram of a helical compression spring. When it is supported, it would be resting here, and similarly there would be one support at the top. Now this is the helical compression spring. Here these are the wire diameters, or I can say that wire which is used to convert it into spring, because springs are manufactured by rolling the wire to get it into a helical shape. So here this small d indicates the diameter of wire, which is 6 mm. Capital D, we have got the value, it was 33 mm. Next, for the spring we have calculated solid length. Solid length was 36 mm. We had calculated the free length, it is 43 mm. Then we have calculated the number of active coils, it was 4. Total number of coils, because 1 and 2, these coils are used to support the spring, they do not take part in the actual compression, so this was 6. And finally we have calculated pitch. Pitch is the axial distance from a point on a spring to the same point on the next spring or the next turn of the spring, and this pitch value we have got it as 8.6 mm. So here with the help of these parameters we can completely define this spring. Even we have calculated the stiffness. Stiffness was 100 Newton per mm. And with all these parameters given, we have completely designed this spring. And in the question, as we see, they had given us that we have to design the helical spring, helical compression spring, for a given range of pressure, and for that given range of pressure which they had given as maximum pressure and operating pressure, we have designed the spring whose dimensions we have denoted on the figure, and with this we complete this design.